The next big idea for the future of carbon cycle is called iron fertilization. So it was known for a long time, maybe from 1930s, that iron could have been a limiting nutrient. It's a micronutrient. In fact, when it's at low levels, it cannot even be measured. But in the 1940s, I suspect, or 60s, John Martin measured it, and then the idea of iron as a limiting nutrient that can be added to drive additional photosynthesis in the ocean to draw down additional CO2 has been proposed and tried, and the success has been mixed at best. So what is the main idea? The main idea is that there are places where primary production, which is measured here as chlorophyll from satellites, is high. So these are the various numbers that you see where the regions are called high nitrate, low chlorophyll regions. So if you look at nitrate concentration in micromoles, this is in milligrams per meter cube, you have high chlorophyll production, and yet nitrate is not all used up. In fact, the nitrate level is tremendously high here, and so on. And the idea is that even though upwelling is bringing lots of nitrates, light is available, primary production is happening, there is substantial production and CO2 drawdown. Of course, here solubility pump or upwelling drives CO2 out of the ocean, but nonetheless, biological pump can take up carbon dioxide here. But the idea is that not all nitrate is used up because the iron concentrations are too low, and it's a limiting nutrient. So they are low chlorophyll corresponding to the nitrate levels that could drive much higher levels of chlorophyll and primary production and CO2 drawdown. This is silicate, so you can see that silicate is also used up. Silicate drives diatom production, which are larger shells which can sink and sequester carbon. All these good things exist. So the main idea is that there is light available in places where you have the solubility pump driving up dissolved inorganic carbon and nutrients into the euphoric zone, where CO2 can be fixed by photosynthesis to create organic matter and oxygen, and then some part of the organic matter is going to be exported out of the euphoric zone, not consumed, and some small percentage is going to make it all the way to the bottom of the ocean, where it's not going to be respired and is going to be sequestered away to be part of the sediment and the longer time scales that we talked about. Of course, a lot of it gets respired back into dissolved inorganic carbon and nutrients. We have, I think, seen the oxygen profiles and so on. And the idea is that to add iron in those key places to drive more photosynthesis, so you can see this arrow got thicker, and hope for more export of organic matter out of the euphoric zone, and the respiration would go up as well as we increase production, but the main thing is to look for increased export production. So this is the idea of sequestration once you get beyond a certain depth. Is that really how it works? Many experiments were done, and in fact there was enhanced production, but you cannot control what blooms. What sinks and sequesters carbon is not the small phytoplankton, but they are the bigger ones. There is some ideas that smaller ones can clump together and sink out anyways, but in the experiments the production turned out to be mostly smaller ones, which basically got recycled and respired and recycled into DIC and nutrients. And the bad news was that the respiration actually created reduced oxygen levels, which is bad for other species which live in the water column below the euphoric zone where photosynthesis happens. So there was no substantial increased or sustained export production. So you cannot really ensure that just by dumping iron you're going to increase primary production. So now more work is being done where you pick locations with such eddies where there is a constant concentration of nutrients and pumping down of water, so that if you dump iron in those places, then maybe the sustaining of the production and export will be more guaranteed. So this is an experiment being planned by the Koreans. I don't know if it happened. I think it hasn't happened, maybe because of COVID and so on. Some have happened, but not all of them. So you can see that they are planning a more designer locations for doing the fertilization of the Southern Ocean. This is an infographic from Woods Hole, which actually in the mid 2005-2006 time scale went on a fairly vocal opposition to iron deposition and iron fertilization experiment. So how will iron addition affect marine fisheries? We will see healthy, thriving ecosystems with plenty of fish, or degraded ecosystems with more nuisance species. So we add iron. Does that mean it'll drive more primary production and up the food chain? Or will it create lots of recycled small particles which will favor these degraded ecosystems like jellyfish? In fact, there are many places where deoxygenation because of the warming and loss of nutrients and so on are actually driving increase in jellyfish population, as well as bigger and bigger jellyfish. There are jellyfish as big as cars that are found in some parts of the world ocean because of the warming and the changes in productivity and so on. So obviously there is no free lunch. Iron fertilization is not at all obviously one of those geoengineering solutions which will take out sufficient quantities of iron. Just like Pinatubo, we have had one experiment in the past which can be thought of as iron fertilization, but if you go see the lectures, podcasts in my Global Carbon Cycle course, you will see that the drawdown of CO2 during the glaciation, so here is the CO2 ppm going from 280 to about 180, so that's 100 ppm drawdown during glaciation. And so we are going back in time, so this is the way to go. So the Eemian to the last glacial maximum, CO2 went down from 180 to 280 to 180 or so, and then during deglaciation in the Holocene it was belched back out. And the idea is that this cooling and the glaciation were associated with spikes in dust concentration, especially over the Southern Ocean. When it's an ice age, the entire atmosphere is colder and drier, reduced rainfall, more dust, and dust has iron in it, so it's called Aeolian Deposition. It's not always clear how much of that dust is really iron and how much of that iron is getting deposited in the right place, how much of that deposited iron is bioavailable in the sense that phytoplankton can actually use it, and so on. And it turns out that iron deposition ideas for explaining this 100 ppm doesn't really work. It may explain maybe less than half of this 100 ppm change. Nonetheless, the idea that enhanced biological cycle could have driven the drawdown of CO2 during glaciation does work, and it does kind of support the iron fertilization idea, which anyway is done and measured. So that's the concept of iron fertilization in the ocean. As we said, it's still not completely clear whether it will be large enough in terms of its ability to take up CO2 into the ocean, and it's unclear what the complete suite of unintended consequences will be. The debate about whether it should be allowed to go on and whether it should be commercialized and so on are still underway, but still some countries are doing these iron fertilization experiments in a small scale. There is no plan right now to do it at a large scale. There was one rogue experiment done off of Canada which led to lots of brouhaha, and I think there is now legal constraints against private companies just going out and trying to dump iron and use that as an offset to sell carbon permits, to say people can pay to offset their carbon emissions by doing iron fertilization. So this is something that has to be always remembered, that rogue players may continue to do these experiments outside the frameworks worked out at international treaties and so on. Okay?